Okay, so as I said, if you have specific questions about certain problems on tests, we can look at those, and we will. I'll have time for that. I'll also just skim through some of those old exams and pick out questions that students have had trouble with, or if you see one like, oh, hey, I need some more on that, then we can do that. But first, let me just summarize what's going to be on the test. We're looking at chapters 3 through 5 in their entirety, so everything from those chapters. What I recommend that you do, this is what I do when I write the test, is you look back at the notes, and I'll pick stuff in the notes and just sort of say, oh, I remember talking about that in class, we're going to have it on the exam. That you look at the old exams. Well, I try not to reuse questions. Some questions I do reuse, honestly, but I try not to. And in fact, on this exam, I think there are only a handful that are reused from past exams. That I will often look at a past question and think, okay, that's a topic that I want to, assess, and so I'll revive it or revise it, revive and revise it. So it's a different question, but still asking the same thing. So as you go through using those old exams, don't memorize the exams, which I know is difficult because especially if you're working them over and over, you're just going to memorize them. But think about the principles behind each question. Hey, Kara. And then if you're a book person, reading through the book, maybe after you've done all the other studying, is probably a good idea. I mean, the book covers the notes, covers the exam, so everything covers the same material. All right, so in chapter 3, that was on work and energy. You need to know the definition of work. Remember, work is equal to F times D. We spent some time talking about negative work. That's when the force and the displacement are in opposite directions, and also about positive work. That's when the force and the displacement are in the same direction. Need to understand the relationship between work and kinetic energy, that if I do work, that I can increase the speed of an object. That kinetic energy, remember, is 1/2 mv squared. Anytime you see an equation like this, you need to understand how changing one variable affects another variable. So for example, here, if I doubled the velocity, that would quadruple the kinetic energy. We talked about potential energy as well. Potential energy is equal to m times g times h. And we talked about conservation of energy. So you can bet that you're going to have a problem where I give you a roller coaster like this, and I ask you, where is the speed fastest or slowest? So for example, if I have a cart like this, its fastest speed is going to be at the bottom. That's where it has the most kinetic energy and the least potential energy. So this is where it's going to be fast. And where it's going to be slowest is where it's at the top. That's where it has the least kinetic energy and the most potential energy. And this is going to be the slowest part of your trajectory. So knowing how the kinetic and potential energy changes will certainly come up on the exam. I gave you several different types of energy: electrical energy, chemical energy, electromagnetic. I've asked questions like that in the past. Which of these is a type of energy? One thing that comes up occasionally is that heat isn't really a type of energy. Heat is really the flow of energy. We talked about that briefly. All right, so remember, heat talks about the transfer of energy from one point to another. It's not really the amount of energy that's contained within a substance. Let's see, conservation of energy. Let me go to the next page. If you want me to pause on something, I'm just sort of giving a summary, then please just say, hey, can you go into that a bit more? Open versus closed systems. In an open system, you have energy going in and energy going out. So you can have energy coming in or going out of that system. In a closed system, there's no energy going into or out of it. And we talked about how as your system gets bigger and bigger and bigger, eventually everything is a closed system. So the universe is a closed system. There's no energy, net energy going in or out of that. Make sure that you know about power. Power is equal to energy over time. In fact, you need to know these basic relationships about, power, for example, and other quantities that we talk about, and then also know what the units for those are. So energy, if you recall, is measured in joules, time is in seconds. So if I ask you what the units of power are, it would be energy per time or joules per second. Also, I could say calories per second. Knowing your units in general will help you on the exam. I might have specific questions about the units of quantities. I'm pretty sure I do, actually. And then also about, just, it will help you to understand the other things. The units of power, by the way, 1 joule per second, this is in your notes, is equivalent to 1 watt. Efficiency. So there is a question about efficiency, and we'll look at some in the past exams. Yeah, Kiara. Power and energy. Power is the rate of energy per time. So, like for example, if I have an object that uses 10 joules of energy in 2 seconds, then I would say that the power of that object is 10 divided by 2, or 5 watts. That it uses 5 joules per second. It's just an energy per time. Okay. Efficiency. We'll come back to efficiency because we'll look at some past exam questions. I know that y'all have questions about efficiency, and that will be on the exam. I think honestly, there's 1 or 2 or maybe 2, maybe 3 questions. But if you miss those, don't miss them because you don't have to. Like, they're not that hard when you know how to use them. But if they freak you out, don't freak out too much because there are only a couple of questions on there about efficiency. You need to know your temperature scales, your Kelvin, your Celsius, and your Fahrenheit scales, not Kelvin scales. You need to know what they're based on. Absolute zero, triple point of water. And then these are the freezing point and boiling point of water. Both of these are. Also know basic temperatures in the centigrade scale. That is the 20 degrees Celsius is room temperature, 37 degrees Celsius is body temperature. And then also know which of these is a bigger scale, or which is a bigger degree. We asked this question in class. So if this is my Celsius scale right here, and this is my Fahrenheit scale, they're both boiling point, freezing point of water. This one is 0 degrees Celsius. This one is 32 degrees Fahrenheit. This is 212, and this is 100. You don't need to know those. Well, no, you do need to know those numbers, at least for the Celsius scale. But also recognize that these degrees, because there are only 100 degrees between those 2 reference points, are bigger than these degrees because there are 180 degrees between those 2 points. So 1 degree Celsius is bigger than 1 degree Fahrenheit. Talked about that in class. And then in heat, one of the big things about heat is the move for calorimetry and phase change. So with heat, as I move from a solid to a liquid to a gas, that I have these heat coming in. This is our latent heat of vaporization. That is, I take a solid, which is at the melting point of that solid, say at 0 degrees Celsius, and I add an extra heat. That's the latent heat of vaporization. And then to go from a liquid to a gas, that's called LF. That's the latent heat of fusion. Make sure you understand the difference between those latent heats. Latent heat of vaporization is the energy to go from a solid to a liquid. Latent heat of fusion is the energy required to go from a liquid to a... No, I got that backwards. I'm sorry. Yeah, thank you. You're going to correct... Who's going to correct me? Everybody, right? This is latent heat of fusion, and this is latent heat of vaporization. I said my busiest day. I'm in class literally from 8 o'clock all the way until just a couple minutes ago. So make sure you understand those. Also, we had this diagram in the book, in the notes, where I have temperature versus energy. It looked like this. Make sure you understand what happens here, that as I move up from my solid right here, so this would be ice, this would be water, and this would be steam, that these latent heats come into play here. Latent heat of fusion, latent heat of vaporization. Let me fix this to you, I'm sorry. This should be F, and this should be V. Okay, that was on page 40-ish, 42. Make sure you know your 3 methods of heat flow: conduction, convection, and radiation. And there was an equation regarding conduction. that had our rate of thermal conductivity. That was Q over T equals K A delta T over D. That is for conduction. And we had convection and radiation. Remember, the primary means of heat loss by the body is radiation, for example. Talked about that. Well, as regarding to the body, you need to understand, listen, everything in the notes is on there. So if I leave something out, I'm just trying to hit the high points. But make sure you go back through the notes because everything is on the exam. But as energy relates to the body, make sure you understand food energy. We talked about where that food comes from. Lipids, carbs, and proteins, which is the most energy dense. That would be fats or lipids are the most energy dense by a factor of 2. And then also work done by the body. Efficiency comes up again there. We'll talk about that in another problem. Okay. Metabolism. Sure you know the difference between BMR and TMR. BMR is the energy to live, right? Not live or live. It's, you know, your body burns energy just operating your organs, thinking in your brain, just sort of living, breathing. And then TMR includes activity plus the BMR, okay? So the TMR is your total metabolic rate, and that's going to be higher, but not much higher than your BMR. Most of your calorie usage is from your BMR. Most calories that you use in a day, more than 2/3, is just from living. We had several examples of how heat loss how the body loses heat. Make sure that you go over those. I'm not going to list them all here, but make sure that you know how the body loses heat or retains heat. Some of those are voluntary and some of them were involuntary, like contraction or dilation of the blood vessels in your skin, shivering, taking a cold shower, drinking a hot liquid, standing in front of a fan. I'm pretty sure I had a couple questions about those things. There are 50 questions, by the way. So as I said, be prepared for most things. All right, that's that chapter. Let's look back at some of the old exams. Mostly you're looking at exams 2. You'll be able to tell them because, well, you'll see the word work or energy. So like, for example, I see here that it starts with work, and it'll be in the same order. They'll have the work and energy questions first, and then we'll progress into the body and energy questions, so about calories and food and stuff like that. So just look for those things. Let's just skim through this. I'm going to look for problems, and then you too. So if you see any, just holler out and say, hey, let's do that one. Here's one with a roller coaster. You're going to see one like that. Here's energy transfer in number 3. Here's just calculating the work done. Number 8 has to do with the work energy theorem. So if I wanted to know how much have I increased the energy, the work is equal to my change in energy, or my change in kinetic energy. So I'm really just calculating the work, which is F times D. That's 10 times 5, which is 50 joules. 50 joules. Here's a question about heat. Remember I said heat is really a transfer of energy, not the energy that's contained in a system. Yeah, Danny?
What about number 4?
Yeah, let's look at number 4. Which of these is a unit for energy or work? Look, I love to ask unit questions. So you might want to go through and just write down all of our quantities and write down their units. I'll do that for this chapter in just a second. But the unit for energy or work is a joule, is a calorie, is a Newton meter. Let's make a separate page and we'll write down all the units, okay? So let's go over here. So regarding this, we had energy, work, heat. These all have the same units. That is that they are joules, or J, calories. That would be capital C cal, or lowercase c cal, or kilocalories even. Any one of those would be appropriate. Also, work, which is a force times displacement, is newtons times meters, or Newton meters. I wouldn't ask you specific heat. Power is one of the quantities that we have in this chapter, and power is going to be a watt, or capital W to abbreviate it, or it's going to be a joule per second, or it could be a calorie per second, because calorie is also a unit of energy. Potential energy and kinetic energy could also fall under this category, so this would be potential energy or kinetic energy. Those are just a type of energy, so they could be measured in that way. Work, I think that's it actually. Yeah, it's just work and energy mainly. I'll do a similar thing for the next chapter. Q fits in here, but remember Q is just heat. Q is heat. Okay, good question. I love units questions. Get a feel for them. Practice through the old exams. You'll see those questions. I feel like if you know the units, you probably understand the concepts too. Let's continue looking through this exam. All right. Here's some stuff about nutrients. Remember, all of these are nutrients. Lipids, carbohydrates, proteins, vitamins and minerals and water are also nutrients. Here's one of those questions I was telling you about. What are the things that you do to be warm or cold? So the body, to stay warm, doesn't sweat. It does shiver. This is usually the one that people get tripped up on, is dilation or contraction of the blood vessels. If the blood vessels dilate, that means they open up and blood rushes to the top of the skin. That releases heat from the body. So 3 is not a way to keep warmer. And then 4 is a decreased rate of blood flow. That's also not a way to keep warmer. Yeah, no, not a way to keep warmer. Sort of have a rough, yeah? Shivering, yeah, is the only way to keep warmer, so D. Which of these is closest to the typical BMR for a person? Just sort of have a rough idea. Oh, those aren't very good. Oh, no, the BMR is the basal metabolic rate. Do you remember what it was? It's around 1,500 is typical. I wouldn't ask that question. Some people it's less, some people it's more. Oh, 1,500, that's the right answer. Okay, so here is a good question about efficiency. This is about the body. The body is about 20% efficient in converting energy from food into usable work. Then if you consume 100 calories of food, how much physical work will be able to perform? So I get 20% out of that energy that I consume in work. So I would say 20% of 100 calories is the amount of work that I'll get. So that's 20% times 100. Whenever I use the word is, that's an equal sign, is equal to whatever my answer is. 20% is 20 over 100 times 100. Cancel that out. That gives me 20 calories. So I get 20 calories. Now, I could phrase it in a different way. Oh gosh, what's another way I could say it? I could say, how much energy is lost in this system? Well, if it's just 20% and I consume 100 calories, I'm actually losing 80 calories. Like, those are unusable. That's just given out in heat of the body. The body heats up and it goes into your BMR. Okay, look at in the past exams. We'll look at some others and we'll see how that works out. Okay, let's see. Let's look at the question. Oh, no. Just stretching. Okay. Means that the body loses thermal energy is through radiation. The latent heat of melting, that would be the latent heat of fusion. Any of these standing out to y'all that you want to look at, or particular topics? Okay, well that's the end here. Here's a basic temperature, 40 degrees Celsius of the human body. Yeah, of course. Oh yeah, that's a good one. Thank you. Who asked that, Kira? Yeah, that's a good one. So following describes thermal conduction. The thermal conduction is 2 kilocalories per second. That means Q over T is 2 kilocalories per second. If the material is changed and the new material has twice the thermal conductivity, what is the new rate? So you need to know what this refers to. And that's usually the thing I'm asking, or that's usually the thing that people have difficulty knowing. The thermal conductivity refers to K. Okay? Alternatively, I could say the new material has twice the area, or it has twice the thickness. So A would be area, and D would be thickness. Or I could say length, too. Okay? And what happens if I double the thermal conductivity? If I double K, that doubles my Q over T. And so whereas I had 2 kilocalories per second, now I'm going to have 4 kilocalories per second. Several questions, not several, but there are 4 to 7 maybe questions that deal with this, not just in this chapter, but in other chapters too. You know the relationship, the mathematical relationship. What happens when I change one of the variables? And it depends if it's a linear or inverse relationship, right? Is it in the numerator or denominator, and is it squared or not? I'm going to take this away. Okay, let's look at the next chapter, which is on sound, speech, and hearing. So in chapter 4, you're going to have just questions about waves. You need to know wavelength, you need to know frequency, you need to know period and speed. Know how to calculate all these things and know how to identify them on a graph. So for example, if I have a snapshot graph, a snapshot, I might ask you to identify one of these. You can tell a snapshot because it has distance measurements on both axes, as opposed to a history graph, which might look the same, but it will have time on one of the axes. Right? History has to do with time, so that's how you know that. With a snapshot graph, I can figure out the wavelength. This is the wavelength. With a history graph, I can figure out the period. That's the period. So the period is the time for one wavelength to pass. I also have some equations that define each of these. These are on the equation sheet, but just sort of know that they're aware. The frequency that they exist. The frequency is the inverse of the period. The velocity is equal to the wavelength divided by the period. And then also I can say that the velocity is equal to the wavelength times the frequency. This equation is really just a combination of these two equations. So make sure you understand those. And then also don't forget that here we talked about how the velocity doesn't change, that the velocity of a wave is only dependent upon the medium. And so if I change one of these, like if the wavelength goes up, that means that the frequency will go down. Make sure that you can identify what wave has a bigger frequency. So for example, this one is a high frequency. This is a low frequency. Okay? Oh, there is one other thing. Don't forget about amplitude. Amplitude is on our snapshot or our history graph. This is our amplitude right here. And remember that your amplitude is related to the loudness of a wave or of a sound, the amplitude. So there'll just be questions just about basic properties of waves and simple harmonic motion. You need to know identify transverse and longitudinal. Transverse, the medium moves up and down. Longitudinal, the medium moves back and forth or side to side. Remember, it's like the wave versus the hug at a football game. Have y'all done that yet, the hug? No cheerleaders in here, right? I don't think we have any cheerleaders. I have a cheerleader in my other class. I'm trying to get her to do the hug at the next football game, but I don't think she's going to do it. All right. Spring constants. Spring constants come up in this too. There was this relationship. Remember, the spring constant was in this equation. This is called Hooke's law. This is the spring constant. If the spring constant is big, that's a really stiff spring. So a spring like in your car, which requires a lot of force to compress it, has a big spring constant, versus a little flimsy spring has a tiny little spring constant. Now the frequency of a wave as a spring oscillates is equal to 1 over 2 pi square root of k over m. Now we didn't really use this equation very much, but I could ask you what happens, for example, if you quadruple the spring constant to the frequency. And because it's under that square root, I would double the frequency. There was a similar equation that we had for a vibrating string, which said that the frequency is equal to 1 over 2L times the square root of T over mu. That's the Greek letter mu. These, make sure you know what these are. L is the length of the string. So longer strings, if L is big, have a shorter frequency. They're higher pitched. I'm sorry, no, longer strings have a lower frequency, they're lower pitched. You understand? If L goes up, F goes down. If T goes up, the tension in the string, tune a guitar, piano, just nobody, just Lauren, right? You're the only guitarist. So if T goes up, if you increase the tension, that means that the frequency goes up. And then if you increase the mass density, that means the frequency goes down. Those big strings on a guitar, they have a lower pitch because they have a bigger mass density. That's why the strings are so different on string instruments. You have different lengths, you have different tensions, and you also have different mass densities to give you those difference in frequencies. Okay. So you know about the speed of sound and the elasticity. Elasticity of a material increases as I go from a gas to a liquid to a solid. And then also, so the elasticity increases as I go from gas to liquid to solid. Also, the speed of sound, because the elasticity increases, also increases. And we saw that borne out in the speed in water, steel, and air in the notes. Sound barrier. The sound barrier is like an interference of waves. Interference of waves occurs when I have waves that add up like this and they cancel out. That was true for noise canceling headphones. Noise canceling headphones operate because of the interference of waves. And that was also true with the whales that we saw. Everybody's favorite little whales add up a wave to kill the helpless little seal, right? Remember, they made the big wave by adding these multiple waves up. That's called interference. Okay, beats. If you recall, if I have two waves that are off by a certain frequency, beats is that wah, wah, wah sound that we heard, and the frequency of the beats is equal to the difference in the two frequencies. So if I have one at 300 hertz and one at 300 hertz, I'll hear a beat that goes once per second. 301 minus 300, and that's a principle that you use to tune instruments. That's what piano tuners do. They just carry around a bunch of, or they used to do, tuning forks that were at a set frequency, and they'd ding the tuning fork and then compare it to the piano string. Also, microphones versus speakers, know how they work. Oh, goodness. Okay, microphone versus speaker. They consist of a diaphragm and a detector. So either something to vibrate the diaphragm in a speaker or something to, well, it's the same. I mean, you have a diaphragm and then it's connected to some electrical signal. So review that, how your microphones and your speakers work. That's true with the ear too. Make sure you know your frequency spectrum for humans from 20 to 20,000 hertz, and the infrasonic and ultrasonic spectrums too. Ultrasound we use for imaging. Infrasonic we can use for a variety of purposes, but animals use it to communicate. Okay, for the A and P section on this, know every part of the ear. I'm going to give you a picture of the ear. Make sure you know how to identify every part in that ear and then also what each part does. So sometimes I'll just ask you for the name of that part, the ossicles, the cochlea, the tympanic membrane, or the eardrum. Make sure you know the different names for those too, like the outer part of the ear had a couple of different names. So make sure you know what those are, the auricle or just the outer, I guess it doesn't have another name, does it? Huh? No, is it pinna? No. I don't think I told y'all that, did I? Yeah, it's just the outer ear. Okay, but remember the outer ear actually includes the auditory canal too. Okay, make sure you know what parts are in what parts of the ear. So what consists of the middle ear, for example? Like for example, the eardrum is part of the middle ear, not the outer ear. So know where that break is. Eustachian tube, know all those parts. And then, oh, so we'll look at a question like this, but logarithms or decibels. We had intensity, which was I. I was equal to the power, energy per time, over the area. So this is watts per meter squared, or joules per second, which is a watt per meter squared. And then we had the sound intensity level. These are two different things, but they're related. With the intensity, by the way, something that I often ask is what happens if you move farther away? And since this is power over area, it's power over 4 pi r squared. So for example, if I move twice as far away, if I increase my distance by a factor of 2, if r increases by a factor of 2, I decrease my intensity by 1 over 2 squared. The sound intensity level has to do with decibels. You know, and honestly, what I want you to understand is that the human ear can detect a very large range of sounds over many orders of magnitude. And I want you to understand how to tell the difference between sound intensity levels. And we'll see a problem in a bit. But let's say that I have 60 decibels to 20 decibels, for example. That is the difference. I have a difference of 40 decibels in the sound intensity level, right? I've decreased by 40 decibels. But in my intensity, I've decreased by a factor of 10 to the fourth, or 10 to the fourth is 1 with 4 zeros after it, by a factor of 10,000. Okay? This is an additive number. That is, I subtracted the number 40 from 60 to go down from 60 to 20. But this is a multiplicative factor. What I mean by that is that if my intensity was say 40,000 watts per square meter, then now I've gone down to 4 watts per square meter because I've decreased multiplicatively, dividing by 10,000. Okay? I'll show you a question. You'll get it tomorrow. It might seem complicated now, but you're definitely going to get it. Make sure you understand earplugs and hearing aids and ultrasound imaging. There were a number of different topics there in the end. You can see a question just sort of about that. What are they called? Those earbuds? Noise canceling headphones. Make sure you understand that. They work by the process of interference. Let's look at the exam. You'll stop me if you see anything here. Okay, so we're picking up here. Now I'm seeing that this is where I'm picking up. It looks like I did have A and P first. Usually I have the physics portion first, but I do try to keep all the categories of questions together. 28. Okay, so what are the speeds of sound in water and steel? Remember, the speed of sound increases as I go from a gas to a liquid to a solid. So what I'm looking for is for where the speed in the solid is bigger than the speed in the gas. I mean, in the liquid. Oh, and then, so I give you the gas right here. So my lowest value should be in the gas. That's 760 miles per hour. My next one is going to be the speed in the liquid. That's 3,400 miles per hour. And then the next one is going to be the speed in steel right here. But it can't be A because it's decreasing as it's moving from water to steel. And that's not what happens. As you move from a liquid to a solid, the speed should increase. And it's also likewise not C for the same reason. So now it's either B or D. And I can tell those differently because the speed of sound in air is 760. So that gets rid of this one because the speed of sound in air should be less than that of water. Okay? In general, this is just good advice for multiple choice standardized exams, which many of you will take. When you read a question, go through and look at the options before you actually plan an attack on how to figure out that question. Because sometimes you can see that there are options that you can just get rid of. There's a question about the intensity. Remember, intensity is power over 4 pi r squared. So here I'm moving from 1 meter to half the distance, what I had before. So I'm halving my distance r. That means I'm going to have 4 times the intensity. I know if I move closer, I can get rid of these 3 answers because I know that the sound isn't going to get less intense. It's going to get more intense. And then I have to figure out which it is between A and E. All right, let's sort of go through some of these. There's your ear. Y'all know your parts of the ear? I think that's probably some of the easiest parts. But make sure you know the name, the location, and what it does. You'll holler out if you see anything. You know the parts of the how we produce sounds too. You can see that figure. Yeah. What's that? 41. Yeah. Okay. So make sure you know these parts. The part labeled 2 is the trachea, right? The part that takes air from your head up here you are up here, down into your lungs. Make sure you know these other parts too. The larynx is number 1. This is the larynx right here. The vocal cords are inside of the larynx. The thyroid, that's not something we talked about. The glottis, remember, is if these are my vocal cords, the glottis is the space in between the vocal cords. All right? When do you have an open glottis? There are 2 instances when you have your open glottis. It's when you're breathing. It's also when you're whispering. Hey, my glottis is open. All right? But when your glottis is closed, when you hold your breath, your glottis is closed for that. It's also closed when you make certain sounds. Right? Remember that video we watched with the lady, the singing lady? In pop music, you close your glottis a lot. You have a glottal stop. When you have hard sounds like the k, that's a glottal stop too, when you actually close your glottis. Okay, good question. Of course, you're going to see a question like number 47. I think actually I give you a figure that has numbers on it, and you have to figure out what is the wavelength. The wavelength is 1 full cycle. So I start here, and I go through a full cycle to right here. The way I can tell a full cycle is, notice right here, I'm going up on the wave. Here, I'm also going up. So don't just go over to here. You have to go 1 full cycle. And so that's going to be, what is this? B is the right answer for this one, is the wavelength. Now, if I gave you some numbers, let's say if this was 0, 2, 4, 6, etc., then the wavelength of that wave would be 4 meters. And I'm pretty sure the question that I gave you on that one does have numbers on it, and you just have to pick off what is the wavelength. Likewise, a similar question would be, what is the period? What kind of graph is this, by the way? Is this a history or snapshot graph? Well, which graph do you get the wavelength off of? with the distance on the x-axis. Snapshot is not time, so you know it's not history. That's the snapshot. Our snap. Huh? History is with time. Yeah, so it looks the same except the x-axis is time. Oh, snap. People still say that? Oh, snap. They do still say it? Oh, Lord. Okay, so let's see, make sure you understand all these same everything, but Bernoulli principle, remember, as the velocity increases, the pressure decreases. Okay. All right, let me clear this. Let's look at E&M, electricity and magnetism. You have any questions, though? Okay, this is longer than I usually go, but there's a lot of material. Is this useful for y'all, just sort of this review? Oh. What's that? 50. Let's see. I like Ani and John, and Olivia's really awesome, but no. Danny, like you, man. You're awesome. Okay. I think there's a freebie on this one. It's always the last option. If you get it wrong, I still give you credit. I usually have one or two students that get it wrong. They just, I don't know, they're just not thinking. Okay, let's look at E&M. You know the properties of charge: positive, negative, like charges repel, opposite charges attract, protons and electrons make up charges. Charge is quantized, that means it comes in particular quantities. Electric forces, remember we have forces, fields, and potential. Forces is given by this equation. You have this on your equation sheet, but I might ask a question: what happens if you double the distance between two charges? The force decreases by a factor of 4. Fields, make sure you know this, okay? Forces, a field, which I use E for that, is a force per charge, or a Newton per Coulomb. The electric field is in newtons per Coulomb. And the potential, which we use V for potential, is going to be an energy per charge. I'm pretty sure there's questions about at least one of these. Energy per charge. This potential can be in volts, or it can be in joules per Coulomb. Sure you know how to figure out the direction of the electric field. So say, for example, I have a positive charge here and a negative charge here. They experience an attractive force, or the electric field between them is in this direction. The way I figure out the direction of the electric field is I imagine a positive charge right there, and I ask myself, what is the direction of the force? It feels a force in that direction, so that's the direction of the electric field. Now expand this and imagine that I have two plates that have positive charges here and negative charges here. They experience an electric field that is in this direction. So I was just expanding that out. If I have two plates of a capacitor, that would be a capacitor, or two sides of a cell membrane that are charged differently. They'll experience an electric field that's in that direction, such that if I put a positive charge inside of that electric field, it will move in the direction of the electric field. Make sure you understand, too, that as I have charges, I like to use this figure. If this is high potential, this is low potential. Remember, it's energy per charge, so we're sort of playing on the idea of gravitational potential energy. So I have a lot of energy per charge at the top and a little energy per charge at the bottom. Positive charges tend to move downhill. That is, they tend to move from high to low potential. Whereas negative charges, which do the opposite of positive charges, move uphill. Pretty sure you'll see that figure tomorrow. Make sure you understand what it means. Do you understand what it means? There are all the equations for those various things. Make sure that you can know what happens. So fields are E equal KQ over R squared. If I change one of those variables, what happens to the others, to the electric field or the potential, which is KQ over R. They all look really similar. They're all on your equation sheet. Just don't freak out when you see them. Okay. There was capacitance. Go back and review capacitance and resistance and current. You might see one or two questions about each of those. Okay. I'm not glossing over them. Those are important. Those are on the test, but we'll see them in the questions. And then electricity in the body. So we talk about static electricity on the surface of the skin, the body conducting electricity, like the E-meter, for example. The E-meter, I don't think that was in your book, but you could see it on the test. It is in the notes, so you could see it on the test. Same with the in-body 230, that you could see that, what it does. You could see that as well. This last section on the nervous system, since we only spent a day on it, there's not a lot of detailed questions about it. So like I'm not going to get into the sodiums and the potassiums and the chlorines and all that. I'm not going to ask you that level of detail. But I will ask you about the purpose of the nervous system, the major parts of the nervous system, the central and peripheral nervous system. I will ask you about the difference between, or the membrane potential, the action and resting potential. Remember, the resting potential is slightly negative, minus 70 millivolts. You don't need to know the number, but that it is slightly negative. And that an action potential is when you have an increase in that. Okay? So I understand that we just did that. I'm not going to have a lot of details. Okay? Like I don't think sodium potassium pump is on there. It's not, in fact. Okay. We'll look at the exam. So here, for example, this is spring 19. I don't have any electricity questions, so you have to go to exam 3. So lots of good questions here. You know, draw the electric field, know what a cation or anion is, know how to make a charged object either negative or positive by adding electrons or taking away electrons, know how to determine how many electrons a cation or anion has. Like if I tell you iron, sorry, it's fuzzy. Iron has fewer than 26. An iron cation has fewer than 26 electrons. Okay, that would make it positive. That sort of thing. What's the Newton per Coulomb? You remember that? A force per charge. What is that? It's a field. Yeah. So make sure you got F, E, and V. Make sure you know those. Forces, electric fields, and potential. Okay, you do need to know the basic parts of the neuron. I'm almost certain that I have a picture of a neuron, and make sure that you know those different parts: the axon, the dendrite, the cell body or the soma, and the axon. Did I say axon? And the axon terminals, right? So dendrites right here, axon right here, axon terminals are synaptic terminals. Danny? Yeah, so this is the brains of the operation. The cell body, or the soma, is what controls the flow of electrical signals. Okay, this is sort of similar, number 17, is sort of similar to the mountain question, where I'm moving from high to low. So this particle would move from high to low and move in that direction. Which you know because the high potential is the positive side and the low potential is the negative side. So it's going to be repelled from that positive side and attracted to the negative side.
What would be number 11?
Number 11, in which part in the neuron does the action potential propagate? That's along the axon. So the axon, the action potential propagates along here. There we have like this wave of the ions moving in and out of the cell membrane as that action potential propagates down the axon. So 3 is the right answer. Whew, it's wearing me out, y'all. There's something about the N-body 230. The N-body 230 and the Scientology thing, the E-meter, both measure resistance. Now, they produce a current, they produce a potential, but they're really measuring the resistance of your body. Units of current right here, units of current are coulombs per second. That is a charge per time. Current here, here's a similar question. Current is energy or charge per time. Know your purpose of capacitors and resistors. We get to focal length, and that gets to the next chapter. Okay, y'all. Resistors limit or resist the flow of electricity. All right. Other questions for me? 25. A circuit consists of a battery and resistor. If you increase the resistance of the resistor, what happens to the current? Resistors resist the flow of electricity. So if I resist the flow of electricity more, the current will decrease. Or you can think about, we had this equation, V equals IR. If R goes up, that means I is going to go down. But I always just think of it as resistors resist or limit the flow of electricity. So if you increase that resistance, it will slow down that current. Okay? If you're ready, like if you've been prepared all along, the test won't be that bad. I think it's, but you know, it's always easy if you know what you're doing. If you don't know what you're doing, then it's going to be hard. But review the old exams. I would reserve some to not review and then just try them. Like, you know, before you go to bed tonight at 8 o'clock, just take that one last practice exam and don't stay up all night. It's not going to help you to stay up all night. Go to bed early, get a good night's sleep. Definitely not go party or whatever you'll do. Like that's the worst thing you could do. Okay, folks. Appreciate y'all coming. We'll do another help session. This is helpful for y'all? Yeah, it's probably good just to review. But, you know, you'll need to do it on your own, too. Practice outside of class.